Welcome to Diffie-Hellman key exchange lesson. So in previous lessons, you saw that digital certificates solved the problem of public key exchange. And that is good when you use asymmetric algorithm. But when it comes to symmetric algorithm, we only have one key. So how do we exchange that key? If Bob and Alice want to communicate with each other and they want to use a symmetric algorithm, how do they exchange one key that they have? Because if they send it over internet through a secure channel, then if someone gets access to that key, then their communication is compromised and it's not secure anymore. Even if you say that what they can do is, for example, Bob can go to Alice and hand over his key to Alice. Then if they have not met each other before, then that's a problem again. How does Alice know that Bob is really Bob and is not someone else pretending to be Bob? So Diffie-Hellman is an algorithm that solves that problem. So Diffie-Hellman is basically an algorithm for key exchange. Now let's go through this algorithm and see how it works and how it solves this key exchange problem. Let's say we have Alice and Bob and these two want to communicate over a symmetric algorithm and they need to come up with a key and let each other know what that key is. So Diffie-Hellman works based on two large prime numbers. As you know, prime number is a number that is divisible by itself and one only. So they come up with two very large prime numbers. Then Alice and Bob both come up with two private numbers. In this case, for Alex, we call that number X and Y for Bob. Now let's put some values to these X and G and Y so that we understand the concept better. And instead of using a very large prime numbers, I'm going to use smaller prime numbers because a calculation is easier, and we're going to use that for the sake of understanding here. So let's say for N we have 11 and for G we have 7. So these are two prime numbers, and X is 3 and Y is 5. So Alice and Bob agree on these two numbers and they can exchange that over a phone or any unsecure channel, that doesn't matter. And even if someone knows about these numbers, that's okay. They cannot use these numbers to come up with a key. The most important thing is to keep X and Y private. Alice keeps X private to herself. She's not going to share that with anyone, including Bob. And Bob is going to keep Y to himself, and he's not going to share that with anyone, including Alice. Now, both of these two are going to use some formulas. Alice is going to calculate an A, and that A is G to the power of X modulo N. In our case, G is 7. To the power of X, X is 3 modulo 11. The result is going to be 343 modulo N. So that means we are looking for the remainder of division of 343 by 11. So the remainder is going to be 2. Bob is going to do the same thing. So he's going to calculate a B, and B for him is G to the power of Y, which is his private number, modulo N. So in this case, we have G, which is 7 to the power of 5. And 7 to the power of 5 is going to be 16,807 modulo 11. So the result is going to be 10. So the remainder of this division is going to be 10. Then Bob is going to send this value to Alice, and Alice is going to send her A to Bob. So they exchange these two numbers. Even if someone knows about this, it's okay because, as I said, they cannot use it. I'll show you shortly what I mean. Now, once Alice receives B, she's going to use another formula to calculate her key. So she says K is B to the power of X modulo N. B is the value that she received from Bob. And Bob is going to say, I'm going to calculate my key, and my formula is A, which I received from Alice, to the power of Y, my private number, modulo N. So for Alice, the value is going to be 10 to the power of 3. That's 1,000 divided by 11. And Bob is going to calculate 2 to the power of 5, 2 is the value that he received from Alice, modulo 11. So 2 to the power of 5 is 32 divided by 11. The remainder of these two equations gonna be 10. So as you can see, both of them came up with a key which is similar. So that's how they exchange the key. Now they have a key, nobody knows about that key, and the key is exactly the same for both of them. Now you may ask that how is this possible? N and G, everybody knew about them, and later B and A also was exchanged over on secure channel. So what if someone like Tom knows about these values? Can he use these values and calculate a key for himself, and that key is similar to Alice and Bob? Well, let's find out. Let's say Tom has a number that's a private number for himself, and that number is Z, and the value for Z is 4. Now Tom's gonna calculate a t, and that t is g to the power of z modulo n. So then Tom's gonna say, okay, I know about g, so g, which is 7 to the power of 4 modulo 11, is gonna give me 3, meaning 7 to the power of 4 divided by 11, the remainder is gonna be 3. Now, in the meantime, Bob and Alice have calculated their A and B, and now they exchange their A and B, and then they come up with their key, which is 10. Now let's see if Tom can calculate the same values. So on Alice's side, Tom is going to use this formula. The B that Alice received from Bob to the power of Z, which is Tom's private number modulo n. So that will be 10 to the power of 4 modulo 11, and the result is 1, which is not equal to what Alice calculated. Now on Bob's side, he's going to calculate another key, and that will be the A that Bob received from Alice to the power of Z modulo n, which is 2 to the power of 4 modulo 11, and the result is 5. Now you can see the two values that Tom calculated are not even close to what Alice and Bob have. He wasn't even able to calculate the same key values on both sides. So that's how Diffie-Hellman works and keeps your key secret. Now there is one way for Tom to get his hand on that key, and that's if Tom acts as man in the middle. And for that, he needs to have two Z's, two private numbers, one for Alice's X and the other one for Bob's Y. And when Bob and Alice exchange those A and B's, then he needs to stop those and provides them with his calculation, so that Alice thinks the value that she gets is from Bob, but in fact it is from Tom, and Bob thinks the value that he got from Alice is from Alice, but in fact that's from Tom again. Now when they come up with a key, then Alice's key is similar to what Tom has on the left side, and Bob's key is similar to what Tom has on the right side. So Tom will have two keys. One is equal to Alice's key and the other one is to Bob's key. And when Alice sends something to Bob, Tom in between receives that, decrypts it, changes the value, and then encrypts it with a key that he shares with Bob, and then sends it to Bob. But in that case, as I mentioned, Tom needs to act very fast so that Bob and Alice don't experience any delay in their communication. Alright, so that's it for Diffie-Hellman, and I'll see you in another video.